Now we're going to make the notion of integral that we discussed in a couple of previous lectures more precise and formal. So let me just do this. From now on, we're going to talk about, so in all these sections and lectures devoted to integration, I'm going to talk about functions that are bounded on a closed interval a, b. So from now on, let's suppose that f is a bounded function on a closed interval AB. So all theorems that I'm going to state should have this in the statement, but instead of writing this over and over again, I'm just going to assume it from the beginning. All right, so let's use the following, let's define the following things. So we're going to define number one, M, capital M, of Fs is going to be a supremum of f of x when x belongs to S. M of Fs is going to be an enthymum, again, for all x that belong to S of the same function f of x. And this is for any S which is a subset of AB. Number two, any collection of points P equal to A denoted by x0, which is less than x1, less than, etc., less than xk, less than, etc., less than xn equal to b. This is going to be called a partition of our interval AB, right? Just like we already said before. Number three, the upper Darboux sum so Darboux here is the name of a person who introduced this notion. Just like a Riemann sum, there is a Darboux sum. Riemann is attributed to Riemann, Darboux is attributed to Darboux. The upper Darboux sum associated with the function f and the partition P is going to be given by the following. U of fp is a sum k from 1 to n m of f comma tk minus 1 tk times tk minus 1. And the lower Darboux sum is basically the same object, except that instead of using capital M, we're going to be using lowercase m. And of course, instead of capital U, we're going to use capital L. So little m. So number 4. So now let's think for a moment about what this thing represents. So what are you doing? You're taking, let me fix the notation a little bit here. We're taking an interval from A to B. We partition it by the points, and I used x's here, so maybe to be consistent, let's replace x's by t's. So I partition it by using the points tk, right, t1, t2, t3, whatever. And that is basically the same thing as what we did when we tried to approximate an area under the graph of the function before, right, where you partition an interval and then you construct rectangles over each subinterval, add areas of rectangles, etc. You get approximation of the area under the graph. So in this case, the product like this, for example, also represents an area of a rectangle. A rectangle with a base tk minus 1 tk and a height equal to capital M of f on that interval. Now capital M is a supremum of a function on the interval tk minus 1 to tk. So then that means that the circled quantity actually gives you the largest possible approximation of the area under the graph of your function on the interval from tk minus 1 to tk. Right? So then if I do the same thing, use the same approach on all subintervals of the partition, then that means that u of fp is going to be the largest possible overestimation of the area under my graph by using the partition p, right? That's the notion that we have discussed already. Likewise, if I look at the lower Darboux sum, everything is exactly the same except that you replace capital M by lowercase m. And a lowercase m is the infimum of your function interval from tk minus 1 to tk. So that means that capital L is going to be the largest possible underestimation. And that means that the area under the graph must lie between the actual area under the graph, must lie between these two quantities, u of fp and L of fp. Okay, so then we said that when we would like to try to obtain the actual value of the area under the graph, or the actual value of a definite integral, what you do want to do is, for example, you look at all possible overestimation of the integral. And what you want to try is to make those overestimations smaller and smaller. How can you do that? You can do that by making a partition finer and finer. So as you make partition finer, overestimation is getting smaller, and ideally at the end of the day, it will go to the area under the graph. So what is the area under the graph then is what should the area under the graph be? It should be the smallest possible overestimation of the area if I consider all possible partitions, right? And so for that, we're going to introduce now a new quantity, or in relationship to that, this number 5 is going to be the following. So the upper Darboux integral is denoted by u of f, and u of f is going to be the infimum over all possible partitions of AB. So it's an infimum over all possible partitions of upper Darboux sums u of fp, right? Again, u of fp is the largest possible overestimation of the integral by using a partition P, and then I'm making these overestimations more precise by making them smaller, right? So the smallest possible overestimation that I can achieve by using all possible partitions, that should be an exact area under the graph. Should be exact value of the integral. And number 6, and symmetric to this, we have the lower Darboux sum, Darboux integral, sorry, which is defined in a similar way, except that now you use underestimations, lower Darboux sums. So that should be, you take underestimations and you try to find the largest possible underestimation. That should be the closest possible value to the actual integral. So it would be a supremum over all partitions of L of Fp. And number 7, so ideally I would expect that, I would hope that the value of the integral that is obtained through overestimations and the value of the integral that I obtain by taking supremum of underestimations, that those are going to be the same thing. So if they are the same thing, then the integral is defined and makes sense. So if u of f is equal to L of f, we say that f is Darboux integrable. On the interval AB, and that the Darboux integral from A to B of f dt or dx, that this is equal to u of f, and of course it's equal to L of f as well, because Darboux integrability means that u of f and L of f are the same thing. And so then the integral that I defined here is called the Darboux integral. Of f over AB. All right. So eventually what we will hope to do is, hope to be able to do is to show that actually this Darboux integral is related to the Riemann integral in some way. And so that will be a subject of one of the subsequent lectures here. Okay, so let's establish some of the properties of a Darboux integral that were going to be useful to us. Not just Darboux integrals, but Darboux sums and all of these Darboux quantities that we just introduced. So number one, if the supremum, in fact, I don't need to say if, because f is bounded on AB, then U of Fp and L of Fp is a finite number. For all partitions P. Right, because if I have a partition P automatically has finitely many points, right? It can have a lot of points, it can have millions of points, but it has finitely many points. And the function is bounded. That means that all quantities capital M and lowercase m, right? All of those quantities are also finite. So that means that the finite sums of finite objects are going to be finite. So both U of Fp and L of Fp are finite numbers. In fact, maybe to make this more English, are finite numbers. Number two. Well, let's see. First of all, what if I do this? Observe that if S is a subset of P, then what can I say about the infimum of S versus the infimum of P? And what can I say about supremum of S versus the supremum of P? Well, what is the infimum? Infimum is greatest lower bound, right? So if S is inside P, that means that P will have more elements than S, right? So if P has more elements than S, if all those additional elements are greater than elements of S, then that means that when I take infimum of S or infimum of P, infimum is not going to be affected, and both infima are going to be exactly the same. On the other hand, if P does contain some additional elements, P does have additional elements in relationship to S, if P contains elements that are smaller than S, then the infimum of P is going to be automatically smaller than the infimum of S. And so that means that always there is this relationship between infimum of S and infimum of P. Infimum of P is always going to be less or equal than the infimum of S, right? Because adding additional elements to the set cannot increase the infimum, but they can decrease the infimum, right? And the reverse of that is that if I add more elements to P, and some of those elements are going to be potentially larger than the elements of S, right? Then the supremum is going to become bigger, right? Because say if P has more elements, but all of those elements are less than elements of S, then any upper bound on S is still an upper bound on P, and so infimum, the supremum is not going to change. But if P also has elements which are greater than elements of S, then this automatically increases the upper bound. So that means that the supremum of P is going to be greater or equal than the supremum of S. So adding more elements might increase the supremum and might decrease the infimum. All right, so then from this, I can also make the following observation. So then if I take M of F, in fact, let me write this as a separate item, because I'm going to use two. So we'll use this observation several times below. So let's make this number 3. So from 2, it now follows that if I take capital M of F, comma AB, and I try to compare it to capital M of F tk minus 1 tk, and likewise if I take little m of F AB and I compare it to little m F tk minus 1 tk. Now, who is tk minus 1 tk? It is one subinterval of my partition of the interval AB. So if I look at tk minus 1 tk, and if I look at AB, tk minus 1 tk is a subset of AB. What is capital M? Capital M is a supremum of my function over the interval, over the given interval, right? So here it is a supremum over AB. Here it is a supremum over tk minus 1 tk. Tk minus 1 tk is a smaller interval, right? So by part 2, what happens to the supremum? Supremum of a larger interval is going to be larger than a supremum of the smaller interval. And the reverse fact is that the infimum of the larger interval is going to be smaller than the infimum over the smaller interval. So opposite inequality sign here. And so therefore from this, what am I going to get? So if I have little m of, well, actually, let's do it this way. Let's take L of Fp. What's that? By definition, the lower Darboux sum is a sum like this. Okay, but then by the fact that I have just established little m over any interval is going to be greater or equal than little m of f over the entire interval ab. So that means that the quantity that I have just written is going to be greater or equal than, I just need to replace tk minus tk by ab. Right, on every subinterval tk minus 1 tk, little m of ftk minus 1 tk is greater or equal to little m of f ab. Well, but then little m of f ab is not dependent on k. So I can pull it out, and I'm going to get m of f ab times the sum k from 1 to n tk minus 1 minus tk minus tk minus 1. Oh well, and what is this sum that we see here? Well, that's a sum of lengths of all intervals in our partition. And those intervals subdivide interval AB. So total length of all subintervals in my partition of the interval AB, total length of those intervals must be the length of the interval AB. How do we show that? Well, this is, if I expand the sum, what am I going to get? I'm going to get T1 minus T0 plus T2 minus T1 plus etc. Plus the sum next to the last one is going to be Tn minus 1 minus Tn minus 2, and then plus Tn minus Tn minus 1. This is something called a telescopic sum, right? So and what is telescopic about it is that most of the terms in the sum will cancel out. T1 goes away, Tn minus 1 goes away, T2 will go away with the next term that I'm not writing here. Tn minus 2 will cancel with Tn minus 2 in the preceding term. And so at the end of the day, you just have Tn minus T0 left. So this is M F AB times Tn minus T0. And then, of course, Tn was B, right? That's the last point of your partition. It's a right-hand point of the interval, and T0 is equal to A. So this is M of F AB times B minus A. All right, so that should be something that is not very difficult to comprehend, and I'm going to draw a picture to show why this must be true, why this formula must be true. But regardless, so then similarly, I can do an identical computation for u, right? And I'll encourage you to do that. So, but for u of fp, this will have to be less or equal than capital M of f of ab times b minus a, right? So to get there, I simply need to observe that if I take capital M, right? So it would be capital M for capital U here, capital M supremum on subinterval, that must be less or equal than supremum of the entire interval, right? So I'm just going to use this formula instead. Okay, and so therefore we end up with the following computation. So u of fp, let me just copy this. So u of fp satisfies this inequality. And L of fp, right, is greater or equal than this. So L of fp is greater or equal than M of f a b times b minus a. And then finally, is there a relationship between L of fp and U of fp? Of course, right? Because they're both based on the same partition capital P, right? And the only difference between upper Darboux sums and the lower Darboux sums is that for lower Darboux sums, I'm using infima of my function over subinterval when constructing the sum, and for upper Darboux sums, I'm using the supremum. Supremum is always greater or equal than the infimum, so that means that automatically we have this relationship. And we can illustrate this by a simple picture. So if I have a function f defined on some interval from a to b, this function is bounded. So maybe it looks like that. Then, of course, the supremum of this function of the entire interval is going to be, in this case, value at b. So the largest rectangle that I can use to approximate the area under this graph is going to be this rectangle here. The smallest rectangle, right, is going to be based on the smallest achievable height. In this case, it's going to be the height at A. So red area basically is this value with capital N, M. Green area is a value with lowercase m, defined on the entire interval AB, right? So that's the red area is actually the largest possible area that I can use with any rectangles, with any number of rectangles, to approximate the area under this graph of f of x. And likewise, the green area is the lowest possible area that I can get by using any number of rectangles on the interval AB. And then if I use any partition of AB, right, so maybe let's do 3 points. Then if I use suprema, the upper Darboux sum is going to be this purple thing here, right? The area of the purple is going to be, if you look at this, strictly less than the area of the red rectangle and strictly greater than the area of the green rectangle. And I'm not going to draw L of fp. I will just leave it up to you. If you draw L of fp is going to be, for this particular partition, so this would be, I guess, T1 and T2. L of fp for this partition is going to be between, again, green area and the red area, and it's going to be strictly smaller than the purple area. Let me just label things here. So label, this is U of fp. This guy is M f of AB B minus A, and the green guy is the largest possible underestimation, whatever. So that's little m here. All right, in the next installment of a lecture, we're going to continue proving these identities and additional properties that will allow us to actually to make sense of a definition of the integral later on.